Welcome to this explainer. Today we are tackling something absolutely crucial. We're diving into the ultimate strategy for mastering the photoelectric effect for the Cambridge physics examinations. Specifically, we are going to be breaking down the notoriously tricky 9702 syllabus, as well as the foundational papers. Look, when you're dealing with these exams, think of it like a high-stakes space mission. Every single calculation must be absolutely perfect for launch. You have a zero margin for error, literally zero. Before we really get into the weeds here, I want you to picture something with me. Imagine two types of students sitting in that dead silent exam hall. Let's call them Alex and Sam. Now, when Alex looks at a past paper question, especially a complex one, he just panics. He overloads his answer with raw physics facts. He just dumps every single equation he's ever memorized onto the page, crossing his fingers and hoping something sticks. But the problem? There is absolutely zero analysis. None. Then you have Sam. Sam, on the other hand, rushes right through. Sam actually knows the material, which is the frustrating part, but entirely misses the command word requirements. They see a question that says, explain, but they just state. I want you to picture their flawed answers, just completely covered in red examiner marks. It's heartbreaking, right? But today, right here in this explainer, we are going to transform those red marks into green check marks. We are going to build a completely bulletproof, foolproof framework so that you never ever leave easy marks on the table again. We're talking total exam mastery.
Okay, so here is our agenda for today. We've got a clear, structured roadmap to guide our mission. First, the exam mastery mandate. Second, core principles and terminology. Third, the procedural framework. Fourth, we'll cover the top examiner warnings. And finally, we will elevate your game with higher-order critical analysis. Let's jump right in.
Section 1, the exam mastery mandate. This is where we set the foundation.
Right off the bat, there is one sheer, undeniable certainty we must face. The photoelectric effect appears in every single Cambridge examination series for the 9702 syllabus. Every single one. It is not an option, it is an absolute guarantee. You're going to see it. So many candidates try to play roulette with the syllabus. They study certain topics really heavily and just lightly skim others, basically hoping the dice roll in their favor on exam day. But if you actually read the principal examiner reports, they tell us a completely different story. The photoelectric effect is consistently used as the ultimate sorting mechanism. It's used to separate the top-tier elite candidates from the rest of the pack. Why? Because it tests multiple cognitive domains all at the exact same time. It tests your basic knowledge, sure, but it rigidly, and I mean rigidly, tests your application and your high-level analytical skills. Securing top marks means you absolutely must conquer this specific phenomenon with complete precision. There is simply no hiding from it. You can't just cross your fingers and hope it doesn't show up. It will.
So what are the examiners actually hunting for? According to the syllabus insights, they explicitly state, top-performing students exhibit connected, conceptual understanding, transferable to unfamiliar contexts. Let's pause for a second and really deconstruct that, because it's vital. Remember Alex, the student who just vomits raw physics facts onto the page? Alex is operating at the absolute lowest cognitive domain. Alex sees a question about incident light on a zinc plate, frantically scribbles down E equals HF minus phi, and then just stops. But the top performer, the student who executes like a seasoned strategist, doesn't just recite facts, they use analytical structures. Think about the Peel framework: point, evidence, explanation, link. They understand the why and the how, not just the what. When examiners throw a completely unfamiliar context at you, like, say, a theoretical new metallic alloy being bombarded by ultraviolet radiation in a total vacuum, you can't rely on rote memorization. You have to connect the core conceptual understanding of photon energy to the work function of that specific new material. It's all about adapting your knowledge dynamically. Before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCS to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
All right, moving on to Section 2, core principles and terminology. Because in this domain, precision is absolutely required.
Let's dissect the single biggest terminology trap that candidates consistently fall into year after agonizing year. We are looking at the critical contrast between threshold frequency and threshold wavelength. Now, threshold frequency is the minimum frequency of incident electromagnetic radiation required to cause the emission of a photoelectron from the surface of a specific metal. Notice the word there, minimum. But then, candidates flip over to a question asking about threshold wavelength and their brains just totally short-circuit. They write minimum wavelength and boom, they immediately lose the mark. Why does this happen? Because they forget the wave equation, velocity equals frequency times wavelength. Since the speed of light is a constant, frequency and wavelength are inversely proportional. Therefore, threshold wavelength is the maximum wavelength of incident electromagnetic radiation that can cause emission. If the wavelength gets even a tiny bit longer, the frequency drops below the threshold, the incident photon energy drops below the work function, and absolutely nothing happens. 0 electrons are emitted. This inverse relationship is exactly where our rushed student, Sam, loses crucial marks. Sam doesn't pause to actually analyze the physics. Sam just mirrors the word minimum from the frequency definition because it feels familiar and right. You must recognize this trap. The energy of a photon is directly proportional to its frequency, but inversely proportional to its wavelength. Understanding this deeply, rather than just memorizing it, is your very first step to that 0 margin for error exam we're aiming for.
Now here is a golden examiner's rule that you need to tattoo on your brain. Always define key terms explicitly before using them in your extended responses. This is a massive, massive area where smart students bleed easy marks. Imagine you get a 4-mark question asking you to explain why a higher intensity light source does not increase the maximum kinetic energy of the emitted photoelectrons. You immediately launch into this beautifully complex explanation about photons. But wait, did you actually define what a photon is? Did you define intensity in a quantum context? Specifically as the number of photons arriving per unit area per unit time, rather than just classical wave amplitude? If you jump straight into the deep end of the physics without explicitly defining the terms of the environment, the examiner simply cannot award you full marks. Think of it like trying to build the roof of a house before you've even poured the concrete foundation. It doesn't work. You need to decode the command word, which is usually something like explain or analyze, and then use that PEL framework we talked about. Your opening point should very often be rooted in a crystal-clear textbook definition of the phenomenon.
This builds directly into what we call the theoretical architecture for top marks. If you look at the principal examiner reports, they show that students who master these 3 specific concepts score significantly higher than their peers. First, we have precise definitions, which we just covered extensively. Second, causal relationships. This means you must clearly articulate that event A causes event B. For instance, you can't just say things change, you have to say that an increase in the frequency of incident light causes an increase in the maximum kinetic energy of the photoelectrons, provided of course that the frequency is already above the threshold. Third, and honestly perhaps the most powerful tool in your entire arsenal, is cross-topic connections. The photoelectric effect doesn't exist in a vacuum. Well, okay, the actual experiment does happen in a vacuum tube, but the theory doesn't. You need to connect quantum physics back to the fundamental law of conservation of energy. You need to contrast the quantum particulate nature of light with classical wave theory. Examiners absolutely love it when you show that you understand the grand, interconnected tapestry of the 9702 syllabus rather than treating it like a bunch of isolated chapters you crammed the night before.
Stop scrolling. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. All right, let's get into Section 3, the procedural framework. This is all about maintaining that 0 margin for error.
This section fundamentally changes how you should view math-heavy physics questions. Welcome to the method mark strategy. You have to remember, marks are awarded for the process, not just the final result. Let's go back to our struggling student, Alex, for a moment. Let's say Alex does all the calculations frantically on a calculator, gets a final answer of 2.4 times 10 to the negative 19 joules, and just writes that single solitary number on the answer line. But what if Alex accidentally hit the wrong button on the calculator? A stray thumb on the keypad? Alex gets 0 marks. It's a complete failure for that question. Now, let's look at the flawless executor. This student writes down Einstein's photoelectric equation explicitly right at the top, HF equals phi plus EK max. Then, they meticulously write down the substituted values for Planck's constant, the given frequency, and the work function. Even if this student somehow makes a catastrophic arithmetic error at the very last second and gets the final numerical answer wrong, the examiner will look at the clear, structured working and award 3 out of the 4 possible marks. This is called systematic processing. The examiners are actively looking to reward you for your logical process. Your working out is literally your insurance policy. Never, ever skip it.
Let's slow down the pacing here for a second, because this right here is your ultimate blueprint. This is a standardized 5-step sequence for solving complex physics problems. Let's walk through it together, almost like an interactive speed writing workshop. Imagine a complex data source sitting on your paper right now. The clock is ticking. What do? Step 1, deconstruct the question.
What is the actual command word? Is it calculate, determine, or show that? They all require different approaches. Step 2, extract relevant data. Write down your knowns clearly on the side of the page. If the wavelength is 400 nanometers, write it down. And don't forget to convert nano to 10 to the -9 right then and there. Step 3, select the analytical framework. Are we using the wave equation to find frequency first, and then plugging that into the quantum equation? Map it out. Step 4, execute with clear notation. This means using the proper, recognized symbols, lambda for wavelength, phi for work function. No messy, ambiguous handwriting that the examiner has to squint at. Step 5, present with correct terminology and units. If you practice applying this exact 5-step sequence to your past papers, you will literally watch the red pen marks transform into green check marks. It builds an automatic rhythm in your brain, ensuring that even under severe, heart-pounding time pressure, your execution remains completely flawless.
Moving right along to Section 4, Top Examiner Warnings. We need to learn how to avoid the most common pitfalls.
I want you to listen to this grave warning directly from the Principal Examiner Report. They wrote, "Candidates consistently confuse key terminology and use the wrong approach for the wrong context." Let's do a quick Find the Flaw challenge in our minds right now. Imagine reading a student's paragraph that says, "When the intensity of the light increases, the waves hit the metal harder, giving the electrons more kinetic energy to escape." Okay, what is the flaw there? Basically everything. It uses the completely wrong approach for the context. It attempts to apply classical wave theory to a phenomenon that specifically, definitively proves the particulate nature of light. An examiner reading that will immediately put a massive red cross through the entire paragraph without a second thought. You absolutely cannot talk about waves hitting harder when discussing the photoelectric effect. You must shift your framework. You have to talk about a higher rate of incident photons, which in turn increases the rate of photoelectron emission, but does not change their maximum kinetic energy. Why? Because the energy of individual quantum photons depends solely on frequency, not intensity.
Let's really break down the top 3 costly mistakes so you can proactively avoid them on exam day. Number 1, wrong approach for context, which we just explored. Using wave logic in a quantum physics question is an instant failure. You have to know which domain you're operating in. Number 2, forgetting to check format and presentation. Now, this sounds kind of trivial, but I promise you, it's catastrophic for your grade. Did the question ask for the answer to 2 significant figures, and you provided 5 because that's what your calculator spit out? Did you forget to convert electron volts to joules before calculating velocity? Presentation isn't just about having neat handwriting, it's about rigorously adhering to the strict mathematical formatting the syllabus demands. Number 3, answers lacking specific contextual details. If the exam question specifies a target metal of potassium, do not just write a generic answer about the metal. Say the surface of the potassium plate. If the light source is specifically a helium neon laser, reference the specific frequency of that laser. Examiners aggressively penalize generic copy-pasted textbook answers. They want to see that you are actually engaging with the specific experiment laid out in front of you. Protecting your grade is as easy as paying attention to these little contextual details.
Finally, Section 5, Higher Order Critical Analysis. This is how you completely dominate the exam.
I want you to notice the exact progression in cognitive domains that examiners use to award those elusive top marks. It's a 3-tier critical analysis framework. At the very bottom, we have descriptive, simply stating what happens. Light shines on the metal and electrons come out. You might get 1 solitary mark for this, if you're lucky. In the middle tier, we have analytical, explaining how it happens using established frameworks. A single photon transfers all its energy to a single electron. If HF is greater than phi, the electron is emitted with kinetic energy. Now this is great, and this is exactly where most good students stop. But at the absolute top tier, the peak, we have evaluative. This requires evaluating alternatives and limitations. For example, why does Einstein's equation specify maximum kinetic energy? An evaluative, top-tier student will explain that electrons located deeper within the atomic lattice require more energy to fight their way to the surface than the minimum work function. Therefore, they are emitted with less than the maximum kinetic energy. Pointing this out shows a profound 3-dimensional understanding of the physics involved. This is the exact mindset you need to cultivate.
Mastering the subject also means you have to critically evaluate the physics data itself. Imagine we're doing a 60-second visual data scan challenge right now. You flip the page and you are presented with a graph plotting the maximum kinetic energy of emitted electrons on the y-axis and the frequency of incident light on the x-axis. A top-tier student doesn't panic. They know exactly how to extract the core trends immediately. They look at it and know the x-intercept is the threshold frequency. They know the y-intercept, if you extrapolate the line backwards, represents the negative work function. And crucially, they recognize instantly that the gradient of that straight line is Planck's constant. But evaluating evidence quality goes even further than that. You need to state assumptions made during the experiment, for instance, assuming a perfect vacuum in the photocell so that the emitted electrons don't collide with stray gas molecules and lose kinemic energy. You need to identify experimental limitations, like the precision of the stopping potential measurement. Truly mastering physics isn't just about blindly performing calculations. It's about interrogating the very data you are working with.
Let's move to our final procedural sequence. When an examiner asks you to compare and contrast, for instance, comparing the emission spectrum of a hot gas with the photoelectric effect, you must execute this flawless comparative analysis sequence. Step 1. Identify similarities and differences. Please don't just do one or the other. They want both. Step 2. Use specific comparative connectives in your writing. Use words like whereas, conversely, or similarly. Using these words literally forces your brain out of descriptive mode and into analytical mode. Step 3. Support each comparison with hard, undeniable evidence from the data provided in the question. Step 4. Draw conclusions on their relative importance. If you write a paragraph using this exact, precise structure, you leave the examiner absolutely no choice but to award you full marks. It removes all ambiguity. It meets the rigorous standard of the 9702 syllabus head-on. Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos.
So, as we wrap up this explainer, I want to leave you with this pivotal question. Are you just memorizing physics facts, hoping for the best like Alex? Or are you executing a flawless analytical procedure like a top-tier candidate? Every calculation, every single sentence you write must be perfectly calculated for launch. I challenge you to take this exact playbook we've discussed today and apply it to your very next past paper. Force yourself to define terms explicitly. Force yourself to write out the full equations before substituting any numbers. The framework is yours now. How high will you let it take your score? Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCS to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCS and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here.